Think about a really complex building, right? A huge grid of beams and joints all connected. Now, what if you could boil down its entire structural integrity into just one single powerful number? Well, that's exactly what a determinant does for a matrix. So let's dive into this architectural way of looking at what they are and, how they actually work.
It's a huge question, and not just in architecture, but in data, physics, engineering, you name it. When you're looking at a complex system, a matrix, how do you get that one quick, definitive answer about its status?
And the answer is this idea of structural compression. The determinant is that single point of truth. It's a scalar value, which is really just a fancy way of saying it's a plain old number that we get by kind of squishing the whole matrix down. And this one number tells a profound story about where it came from.
Okay, but before we can even get this number, there's one non-negotiable law of architecture we absolutely have to follow. You can think of it as the golden rule for determinants.
And that rule is all about perfect symmetry. You can only calculate a determinant for a square matrix. That means it has to have the same number of rows and columns, like a 2x2 or 3x3. If you have a non-square structure, nope, it's rejected. You just can't find a determinant for it. The system has to be balanced.
So, assuming we've got our perfectly symmetrical square matrix ready to go, how do we actually find this magic number? Well, we can think of it like a level-up guide, starting with the absolute basics and then building our way up.
Level 1 is, well, it's about as simple as it gets. For a 1x1 matrix, the structure is already totally distilled. The determinant is just the number inside. So the determinant of a matrix that only has the number 5 in it is, you guessed it, 5. Easy enough.
All right, let's level up to the 2x2 matrix. For this, we use what I like to call the X-ray method. We find the product of the main diagonal, that's A times D, and then we subtract the product of the other diagonal, B times C. So the formula is just AD minus BC. Simple as that.
Let's see it in action. It makes more sense that way. So we've got our matrix here. The positive diagonal is 3 times 5. That's 15. The other diagonal is 2 times negative 9, which is minus 18. Now the key is we subtract the second one from the first. 15 times negative 18. And you know that double negative becomes a positive, right? So that gives us our final extracted determinant of 33.
So what happens when we level up again to a 3x3? Well, this is where things get interesting. Our simple little X-ray method just doesn't work anymore. You can see it right here. A single cross pattern leaves a bunch of the elements completely untouched. Our method just isn't big enough for the job. We need to expand our toolkit.
And the solution is, honestly, it's just so brilliantly architectural. We basically erect some temporary scaffolding. To handle a 3x3, we just copy the first 2 columns and stick them right next to the matrix on the right-hand side. This gives us the bigger workspace we need to make sure every single element gets included.
Now, with our scaffolding all set up, we can weave our diagonals. We trace 3 full positive diagonals going from the top left to the bottom right, and then 3 full negative diagonals going from the top right to the bottom left. Now look at that! Every single number in the original matrix is part of the calculation. Nothing gets left out.
Let's walk through a real example. First up, we calculate the product of each of those positive diagonals and add them all together. Here, that gives us a positive sum of minus 469. Got it? Okay. Then we do the exact same thing for the negative diagonals, and we get a sum of minus 2. And finally, just like we did with the 2x2, we subtract the negative sum from the positive sum. So negative 469 times minus negative 2 gives us our final determinant, negative 467.
Okay, so we just did all that work to get one single number. You might be asking, what's the payoff? Why should I even care? Well, this is where the determinant reveals its most important job. It's a singularity diagnostic.
So here's the bottom line. That final number is basically a health check for the matrix. If the determinant is 0, the system is compromised, it's broken somehow. We call that a singular matrix. If it's any other number, positive, negative, doesn't matter, the structure is stable and robust. That's a non-singular matrix.
And this image just illustrates that concept perfectly. A determinant of 0 means the structure has, in a way, just collapsed in on itself. The pieces aren't independent anymore. But a non-zero determinant? That means the structure is sound. It's standing strong.
Here's a perfect example of that collapse in action. After we do all our math, we find that the sum of our positive diagonals is 42, and the sum of our negative diagonals is also 42. So when we do that final subtraction, 42 minus 42, what do we get? A big fat 0. That is the clear signature of a singular matrix.
So let's just bring this all together. We've got on this whole journey from a complex grid of numbers all the way down to one single, really meaningful value.
We've seen the whole framework, right? From the super simple 1x1 to that X-ray method for a 2x2, and all the way up to building that scaffolding for the 3x3. Each level is just designed to handle a bit more complexity than the last.
So in the end, you can really think of the determinant like a funnel. It's the ultimate condenser. It takes all this multidimensional complexity and just reduces it all down to a single point of truth, a final check that tells you if your structure is sound or if it's singular.
And that leaves us with a pretty fascinating thought, doesn't it? If just one number can reveal so much about the stability of an entire system, what other incredible, hidden truths are just waiting to be uncovered, all encoded in the elegant language of mathematics?